Hello and welcome to another Stephen Mendes video. In this video we're looking at transient DC analysis of RLC circuits that contain capacitors and inductors and resistors. Well, we know that the students want to know how to solve these problems with initial conditions. That is when the capacitor has some charge and the coil may have some current through it at the beginning of the problem or when the switch is thrown. We use the t equals 0 to signify the start of our analysis of the charging or discharging action and be able to determine the transient voltage over time by a mathematical expression. So our simple serial circuit, we're looking at the serial circuit first, has in a coil, a resistor, and a capacitor. We've put some values there in a voltage. Now the initial condition before you throw the switch to apply the 10 volts is that the capacitor has 6 volts across it and the coil has 2 amps flowing through it. And we are asked to find V for t greater than 0. So that means after the switch is thrown, there will be a further increase in the charge on the capacitor from 6 volts up to the maximum of 10 volts, at which time the current will cease entirely. So that we are going to solve that problem now with a mathematical expression in terms of time. And that is why it's called transient or time varying behavior on a DC circuit. The first thing we need to do is to write a Kirchhoff's voltage law around the loop. So the 10 volts is applied at t equals 0. And around the loop we have, as you can see, the expression for the various voltages. So those 3 or 4 terms there are voltages. We have just the derivative of I, the current, because the coil happens to be 1 Henry. But that should read L di over dt, because that is what relates the current in the coil to the voltage across the coil. Then for the resistor, it's simply Ohm's law. So we have, here you can go and see it, we have V equals IR, and I is shown, and the R is 2, as shown in the diagram. So that also is a voltage term. Then we have this term here, which represents the relationship between the current and voltage inside of the capacitor. We are basically integrating the current across time, and we have the capacitance here. And we have, that's 1 over the capacitance. That's why it's 5 instead of 1/5. 1 over C, we integrate the current, and that gives us, the whole term gives us the voltage. We also have to include the voltage that it had initially, so that all of that adds up to 0. So that's how we do that. And there I've just indicated that for you. And just remember to put the initial voltage into the loop and you should be good to go. Now we differentiate that whole expression, and after differentiation we get a second order differential equation as shown there. So the second derivative at the front comes from the coil, because we've differentiated again, and then we differentiate the 2i, so that actually comes, the 2 is a constant, so that really is just differentiating the I. And finally, when we differentiate the integral, we just get 5i. So the characteristic equation for that differential equation is simply a quadratic equation. S squared plus 2s plus 5 equals 0. So we use the quadratic formula on that quadratic equation, and we end up with a complex pair. Since we have a negative number under the square root, and that merely means that the solution is going to be underdamped or oscillatory and will contain sine and cosine terms. There's a very specific solution that we apply depending on whether it comes out underdamped, overdamped, or critically damped. And the solution we use for underdamped is shown there. Now, the cosine and sine frequencies, omega equals 2, is shown there, and the 1 is in the exponential term. So that is why we have it written that way. The J2 goes into the angle of the sine and cosine, and the real part goes up there in the minus t. The minus 1 is the reason why we have a minus t on the exponential term. Now, what I've shown there is another way to do this. Instead of using the actual values of R, C, and L in the quadratic formula, we can simply use the R, C, and L. This part up here shows us quickly whether we're dealing with complex roots or not, because if C is less than that, then we're dealing with complex roots. This part gives us omega O, or the natural frequency, quickly from the L value and the C value. This part gives us the damping coefficient quickly from the R and the L. And the damped frequency, omega D, we get from the omega O and the alpha. So we can do this calculation here in red and plug in the numbers down here as well. So you don't have to do both. You can either use the quadratic formula and solve the quadratic formula, or you can use the RC and L values with these formulas and still write in the correct numbers into your solution, your mathematical solution. Now, by inspection of the actual circuit, we can see for ourselves that when the capacitor is fully charged, current will cease and the actual value of V will be 10. But the solution that we have above makes no provision for that, because the exponential term is going to die out, and therefore V will go to 0, and that's not the steady state. The steady state is actually 10. So we have to actually add that term of 10 to the answer to make sure that V ends up as 10. After this whole thing has died out to 0, we will have V as 10, which is the correct solution. So we say that the forcing function, or the 10 volts DC, is just added into the solution in that manner. So that's easy enough for you to do. Now, at the start, we have V as 6. So what's going to happen is that the capacitor is going to charge from 6 volts up to 10 volts starting at t equals 0. So the t equals 0 there means that we can set t to 0. Set t to 0 in this expression up top here, which will cause the sign to drop out, because sine of 0 is just naught. So we will only have the A1 and the 10. So basically we can set the VO to 6, And then we can quickly find out A1. So A1 is minus 4. So that's easy enough. We've just found the A1 in a hurry. To find the A2 now requires to use the current, that initial current that we were talking about at the beginning. Now, we can take the capacitor expression. This capacitor expression is what relates the voltage across the capacitor to the current. So the initial current was 2 amps. And here now, we want to find out what this is for C. So we use the value of C we have in our thing, and we divide 2 by that, and we find out that our dV over dt is equal to 10. Now that's good for us, because the next step now is to differentiate the solution so that we use the solution and we get the dV over dt that we desperately need. And we are still operating at t equals 0. And at t equals 0, all the signs are going to drop out. But since when we differentiate sines and cosines, they reverse. That is, we get a cos for a sine and a sine for a cos. We are now able to find A2 using this method. So when we go through that long differentiated expression plugging in a t of 0 in all cases, we end up with our dV over dt equal to 2A2 minus A1. And we already know what A1 is, so now that helps us to find A2, and it turns out that A2 is 3. Now, we have A1 and A2, and we are in a position to write our total solution and final answer. Thanks for watching, and see you in the next video.